Hi everybody, our project is on impairment-aware human building analysis, and our group members are Sanjeet, Kinjal, and Brian. So what is the problem? In crowd simulation and evacuation research, it really aids in the decision-making process for evaluation of floor plans. But throughout this research, it's really only focusing on those able-bodied humans who don't have disabilities or handicaps, and it's very generalized. So these spaces are really only evaluated as satisfactory for a subset of the human population, when in reality, 1 in 4 American adults actually have a disability. So we're looking to combat that and try to create more diverse crowd types. So our motivation for actually doing this project is to create more realistic simulations with heterogeneous crowds, including humans who are, for example, in a wheelchair or who have visual impairments and have to just walk slower. And through the use of this more realistic crowd simulation, further research along the line can reassess if buildings are truly satisfactory and suitable for human inhabitants without using their generalized and homogeneous crowd they originally used. And this can further be applied to human building interaction, floor plan analysis, and evacuation scenarios.
So some of the main challenges on this project was getting handicapped agents in wheelchairs to evacuate efficiently, and also getting realistic evacuation during drills to allow for better planning procedures. Some of that could involve fire drills, actual fires, emergency evacuations, and more.
Okay, when it comes to prior work, there have been in the past a lot of human building interaction models, and so currently it is very common to use different mathematical and computation models in order to analyze and assist in architecture and urban design. Some applications of these models are that they are used in order to analyze the cost, energy, and structure when designing buildings. Our project is actually going to be a subset of this human building interaction, and we are going to be focusing on a evacuation model. And now there have been a lot of other evacuation simulation models in the past. Some of these includes other evacuation simulation models such as Way Out, Building Exodus, Exit 89, and more. Basically what these do are they simulate various scenarios for evacuation under different circumstances, like emergencies, blocks exits, as well as toxicity. Basically their main purpose is to analyze safety and effectiveness of different buildings for evacuation. And to the right, there, just as an example, there's a picture of an evacuation model being used to simulate a cinema that is on fire. However, there are some limitations on these work, and the main one that we saw was, despite the fact that there is a large amount of previous models in evacuation modeling, handicapped agents have largely been ignored in these models, and the focus has mainly been on the fully abled population. We believe that human building design should also keep handicapped peoples in mind, as they require a lot of different resources, especially during evacuations, such as ramps instead of stairs, and they would need more space in order to move, and may move slower than a fully abled person. So basically our proposed approach is to create an evacuation simulation model that accounts for the handicapped population as well. So basically what our model will do is it will be able to simulate a mixed crowd of both able-bodied and handicapped agents evacuating from a building, and then the building would be analyzed on metrics of times it takes for evacuation and the number of collisions that would result during the evacuation, and we would test this across many different floor plans in order to analyze these different floor plans.
Now, to understand our actual simulation and our methodology, we're going to talk about the agents that we're using in our scene. The first agent of 3 is our able-bodied agent, which has normal characteristics such as a standard velocity and acceleration. Our second agent is a handicapped agent, which is wheelchaired. This wheelchaired agent will have a reduced velocity and acceleration, and this will be varied between the different wheelchaired agents we have in our scene. This is to produce more realistic results and, have more proper data for our simulations. Our last handicapped agent of 2 is our visually impaired one, and this agent has also a reduced velocity and acceleration, but as we mentioned with the wheelchair agent, it will also be varied, so each different visually impaired agent will have a different velocity and acceleration to produce more realistic results for our simulations. Normally, the visually impaired agents will have a velocity and acceleration a little less than our wheelchaired agents due to the fact that they do move a little slower.
Okay, and now I will be going over the different scenes that we used in order to test our model. And we end up creating 3 different scenes in order to test our model. One being just the default one we came up with at first, which is the basic mall scene. And then 2 others that had additions such as ramp to the mall in order to make it more accessible for handicapped individuals. So pretty much our first scene is just your basic scene. So as you can see, there's stairs going from each floor. However, that would not work for our wheelchaired agents since they are not able to traverse downstairs, so they would need some form of ramp. So in order to better get a view of the wheelchair agent traversing the different floors, we made 2 other scenes as well, and there's both slightly different in order to test which scene architecturally is better for evacuation. For our second scene, we ended up changing it, which is a small ramp scene. Before, the ramps were in different locations between the small ramp scene and the large ramp scene, making for an unfair comparison between the two when it came to the statistics. So what we end up doing was modifying the large ramp scene and just simply making those ramps smaller. So in essence, the small ramp scene just became the large ramp scene with smaller ramps. So same layout, but with smaller ramps. And for our last scene, we simply added large horizontal ramps in between floors as opposed to the small ramps in between floors that we added in the other scene. The logic behind this is that multiple wheelchair agents can go down the large ramps as opposed to the small ramps where only one wheelchair agent can go down at a time. We wanted to see if this would help reduce traffic when it comes to large crowds exiting a building, as there wouldn't be a bottleneck at these smaller ramps that would occur in the other scene because there's a larger space in order to traverse between floors.
Now we're going to walk through the evacuation. So first we added the 3 different types of agents in the same environment traveling towards a specified destination. And as we mentioned before, these 3 different agents are our able-bodied agent, our visually impaired agent, and then our wheelchaired agent. The 2 handicapped agents included in our scene are the wheelchaired agent and the visually impaired agent. Second, we utilized the social force model for agents within the scene as an obstacle avoidance technique. And third, using the evacuation situations, we've simulated 5 different scenarios in 3 scenes for a total of 15 total simulations. And the different ratios that we've used for the 5 different scenarios are as follows. 1 normal to 0 handicapped, 2 normal to 1 handicapped, 1 normal to 1 handicapped, 1 normal to 2 handicapped, and then 0 normal to 1 handicapped. As we varied these different ratios, we wanted to compare the time that it took for all the agents to evacuate successfully. As a note, we wanted to model a more densely populated mall scene for more realistic results. So in each scene and simulation, we have a total of 153 total agents. As we've discussed before, we have 153 agents per simulation since we wanted to model a more densely populated mall scene. And this is a 2-to-1 simulation where there are 2 able-bodied agents to 1 handicapped agent. As we have mentioned previously, the handicapped agents include wheelchaired agents and also visually impaired agents. And it's important to note that our handicapped and visually impaired agents are all moving at different speeds and velocities and accelerations to be more realistic in terms of the data. And additionally, although we have a certain amount of handicapped agents we have within the scene, we have a random distribution of wheelchaired to visually impaired, as we wanted to make it as realistic as possible within the scene for the agents and the data. How we obtain the results were by keeping track of the count of evacuated agents and also having a timer. So the evacuation counter is the total number of agents that have evacuated, which is equivalent to handicapped agents and normal agents. And the handicap timer is just for handicapped agents, which includes the agents on a wheelchair and the ones who are visually impaired in our scene. Through this, we've created graphs for our simulations, which will show in the results for the 15 scenarios that we had done. Now we will be discussing the results for scene 1. As a reminder, in scene 1, all wheelchaired agents were required to be on the first floor since this scene did not have any ramps, but only stairs. So for the first simulation of 1 to 0, which is 153 normal-bodied agents to 0 handicapped, it took around 55 seconds. And in contrast, for the last scene, we can see that it took around 159 seconds for all of our handicapped agents to exit, because that was the 0 to 1 ratio. Within each different simulation, we've seen that time increase as the number of handicapped agents also increase. This was expected since the handicapped agents will have a slower movement rate and also take longer to exit and successfully evacuate the building. This causes more time needed for the total population with a mix of normal and handicapped or just handicapped to leave the building. Just from scene 1, we're able to see that, yes, if we do include handicapped agents within the scene, it will take longer for all the agents to evacuate as compared to a more homogeneous population of just normal-bodied agents.
All right, so here we have the results regarding the number of agents we have evacuated versus the time. So we decided to display everything in bar graph, and everything here is small ramps from scene 2. So the reason we did bar graph is because it accurately represents more about the number of agents we have evacuated versus the time, along with more accurate analysis of our data. So the first graph I will talk about is 1 ratio to 0. So basically, in about 69 seconds, we were able to successfully get a total of 150 agents evacuated. A majority of them were at first non-handicapped, and few of them were handicapped, but majority were non. But as we go more and more, so from 2 ratio to 1, so we had actually a more number of mixed agents that were handicapped and non-handicapped. So in about 174 seconds, we had a total of 150 agents evacuated. And as you see, the data grows more and more. It shows number of agents that are non-handicapped and handicapped, such as wheelchair and blind agents. And then 1 ratio to 1, the number still continues. It's a mix of non-handicapped and handicapped agents. It took about 180 seconds total to evacuate everybody. 1 ratio to 2 underneath represents how much more time it took. So we had a little bit more increase in handicapped agents, actually a lot more increase, because if you look at it here, apparently it took 186 seconds to get most of the handicapped agents out of the building, while the total is still 150, but a majority of them are handicapped agents over non-handicapped. And then 0 ratio to 1, all the agents there were purely handicapped. It was all handicapped agents, and it took a lot longer, at least 189 seconds, 3 seconds longer compared to the previous, to get all the handicapped agents out of the building. So here, all the agents we had, 150 of them were all handicapped. So overall, with small ramps, it took at least 189 seconds for 150 handicapped agents to be able to evacuate out of the building.
And I'll be discussing the results for the third scene, the large ramp scene. So the large ramp scene stayed the same as previously, whereas the small ramp scene was modified, changed to be a modified version of the large ramp scene instead of with smaller ramps. So in essence, it would have the same layout with smaller ramps. Now, as you can notice, the total time it took for agents to exit the building stayed about the same throughout all the handicapped runs, but that was generally seen as a because of a few, one or two, handicapped agents at the top floors whose time it took to exit the building stayed relatively the same throughout each simulation. Now, one of the important things to notice that during the beginning parts of the evacuation, the slope for these simulations tended to be larger than the slopes of uh, the small ramp results, which means in essence that the rate at which agents were exiting the building were higher, which can be attributed to the lack of bottlenecks that occurred uh, during the small ramps where agents were being held up by other agents. With the large ramps, more than one person could go down the ramp at a time, thus allowing less of that bottleneck there. And I think that was the most important thing to take out of it. Thanks.
So the results here describe the number of time it took from scene 1, scene 2, and scene 3. So we ran different iterations of simulations. So as mentioned in scene 1, this is the original and no ramps. The first simulation for scene 1 took 55 seconds. Then second one took 142 seconds. Third one took 144 seconds, and 146 and 159. So as you see, as we ran more iterations of simulation testings for impaired people, handicapped, and normal agents with more people in the environment, it took more times, and this is with no ramps for both normal agents and handicapped. Scene 2, it for small ramps, it apparently took handicapped patients and impaired patients more time, from 69 seconds to 174 seconds, to 180 seconds, 186 seconds, and 189. So scene 2 ended up taking um, a little bit more times compared to scene 1 with small ramps, but again, we had more large crowds for evacuation. And then scene 3, so this was large ramps. The first two test scenes for simulation took between 183 seconds and 180 seconds, and then eventually there was like a decrease to the third test. It was more 177 seconds, and then increase again. Eventually, it went to 188 seconds. But scene 3 of large ramps, we were able to see overall more efficiency in evacuations for handicapped agents, impaired agents, and normal agents. So overall, for the evacuation, as the amount of handicapped agent increased, the evacuation time also increased. Unsure and possibly anomaly in scene 3 timings is another thing, so possibly that's negotiable considering um, amount of time we give to the agents to evacuate. And then accessibility to all floors has a trade-off for larger evacuation time, so that's with adding ramps. So if we add more larger ramps for more large crowded handicapped people, that could add more time. So to conclude this project, based on all of our contribution, Kinjal was responsible for managing modeling plus animating able-bodied and handicapped agents, setting up the initial environment, which includes nav mesh and agent navigation, setting up handicap counter, and evaluating all the simulations based on different iterations and different scenarios. My contribution mainly involved implementing social force modeling, experimenting with additional agents, AI animation plus AI control, setting up timer plus evacuation counter, and evaluating metrics on simulations. Brian's contribution involved managing modeling plus animating able-bodied and handicapped agents, so working with Kinjal on that, along with also working with her on navmesh and initial environment, creating two scene variations, and running all the evaluated simulations. So he actually created the small ramps and large ramps, which was able to give us more information. Okay, if there's ramps added for handicap agents, then it should be able to help make a difference. So overall, putting all this together, we implementing our works together, we were able to make three different situations with three different scenes for agents in situations involving just stairs for all normal and handicapped agents, small ramps, large ramps, and getting more information to see what's the best and cost effective solution. Thank you for listening to our presentation.